Nick is an assistant professor at Warwick that specializes in post-quantum proof systems. And recently he has been doing some very nice work that touches on the topic of one-shot signatures that he's going to be telling us about. So I should say normally, like his Warwick is not too far from Edinburgh, but this academic year he's visiting professor at NYU. And as I understand, he's
Okay, so I've been asked to start. I can't hear anything, so I hope that I'm not like speaking over people. So thanks to Justin and Agalos for inviting me, and for everybody who put this together. I think this is a great event, and I'm sorry that I can't be there in person. So ordinarily I'm at the University of Warwick at the moment. Which is a relatively short train ride, but at the moment I'm in New York City, where it's relatively early in the morning, and so I'm thankfully I have the opportunity to present remotely, so I appreciate that. So today what I'm going to be talking about is some recent work with Marcel Dalagnol, who was a PhD student at Warwick and now is a lecturer at Princeton, on ways to construct a way to construct potentially one-shot signatures. Right? So one-shot signatures are really wonderful, but we don't have we don't have any constructions of them really at all. They're not even candidates. And so, this is not this talk is not really going to change that, but it's going to show a relationship to other areas of quantum cryptography that might lead to some ideas about how to build these things. Okay. So what we're going to, the object we're going to be looking at today is something called a collapsing hash function. I should say that I've been asked to keep this the presentation short so that we can have a lot of discussion. So that's what's going to happen. So what is a collapsing hash function? So here is a somewhat simplified definition of it that is not accurate, but will give you an idea of like what the what the property is that we're looking at. So a collapsing hash function H has the following property. So if I start with a uniform superposition over inputs to the hash function, and then I apply the hash function in superposition, so then I have this uniform superposition over x and h of x. Then what I can do is I can perform the following experiment. So I can measure the second register of the superposition, right, and I get out a classical y. And then what I'm left with on the first register is the uniform superposition over x such that h of x is equal to y. So that's sort of an experiment I can do. The other experiment that I can do is I can measure the second register and then measure the first register, and then I'm left with just a single classical x, right? So basically just a random x such that h of x is equal to y. So these are sort of two quantum states. Each of them is mixed, right? But the first state is in some superposition, and the second state is collapsed to some x. And we say that a hash function h is collapsing if these two states are indistinguishable, the blue and the orange state. So the uniform superposition of x's that map to y, and the a random x that maps to y. Okay? So these two quantum states are indistinguishable. So why do we study this strange experiment. Well, I guess one thing so to start off with is that collapsing implies post-quantum collision resistance. So I should say this definition was introduced by Dominic Unruh in 2016. So collapsing implies post-quantum collision resistance. So if the hash function is collapsing, then a quantum computer also cannot find two inputs that map to the same output. But moreover, it kind of succeeds where collision resistance fails. So it turns out to be the right strengthening of collision resistance for a bunch of cryptographic applications, like protocol applications of hash functions, including things like zero knowledge proofs and succinct arguments. So when you try and prove security of a number of cryptographic primitives in the quantum setting, using just post-quantum collision resistance, then you get stuck, and you get stuck in the proof, and it turns out that collapsing is kind of the patch that you need to make everything work. So the kind of big open question, I think, in this area is, does post-quantum collision resistance imply collapsing by itself? So is every post-quantum collision resistant function, hash function, also a collapsing hash function? And this question is kind of a win-win type question. Because if the answer is yes, then we have sort of more faith in our hash functions, right? So collision resistance becomes then enough, post-quantum collision resistance becomes then enough for proving post-quantum security of protocols. I should say that the answer is known to be yes for some class of CRHFs. I'll talk a little bit about that later. That satisfies some sort of structural condition due to Mark-Jandry. If the answer is no, then we actually get, I think this is probably the more interesting case. So if the answer is no, if we can find a post-quantum CRHF that is not collapsing, then we're going to get cool quantum cryptography. And this was first established by Mark again in 2019. So it turns out that this is enough for something called quantum lightning. And in this paper with Marcel, we showed that actually it's enough to get this stronger object of one-shot signatures that we're all talking about today. Okay. I don't know if it's possible for you guys to interrupt me, but if you want to interrupt me, then feel free to. I'm happy to take questions during. Okay. So I'm going to present quite briefly how this result works. Why is it that sort of non-collapsing hash functions imply one-shot signatures, and then give a couple of directions about where I think we can go from here. So how does the result work? So what we do is we write down this equivocation game. And it's a very simple game between an adversary and a challenger. So the adversary sends a bit string y, which is supposed to be the output of the hash function, and an index I, which is an index of a bit in the input of the hash function. The challenger sends a bit b, uniformly random. And then the adversary responds with an x, and the challenger accepts if, firstly, x is a preimage of y under age, and secondly, the ith bit of x is b. Okay. So it's fairly straightforward to see that you can easily win this game with probability 1/2, right? If b happens to be like you just hash x to y, and then if b happens to be x sub I, then you win, right? As the adversary. On the other hand, it's also not too hard to see that if H is collision resistant, then a classical adversary will win with probability at most like 1/2 plus negligible. Okay? Because you can sort of rewind, and you can then, like, if the adversary is winning with probability substantially more than 1/2, then you can rewind and you can obtain two x's where the ith bit differs, and so that's a collision in the hash function. Okay. So I guess interestingly, if H is collapsing, then you can show that actually a quantum adversary wins with probability at most 1/2 plus negligible. Okay. But the really interesting thing, and the thing that I'm going to be talking about, sorry, I guess the first interesting thing, but not the thing that we're talking about, is that on the other hand, if you can kind of break this barrier, so if you can get a quantum attacker that wins with probability greater than a half plus some inverse polynomial, then you can transform this into a one-shot signature. And this is sort of using some sort of amplification techniques that have been developed recently in the literature, and then some of the machinery from the one-shot signature paper to go from like some equivocal commitment or equivocal hash function to one-shot signatures. So the part of the part that I want to talk about today is that this adversary, the existence of such an adversary, is implied by H not being collapsing, subject to the usual caveats about like infinitely often versus almost everywhere. Okay. So how does this go? How do we show this implication? So it's pretty simple. So I want to actually like share with you basically the whole proof. So suppose that the hash function is not collapsing, right? So we have this experiment. What this means is that there is this pink measurement, quantum measurement, which distinguishes the blue and the orange states. Okay? So what that means is that for the blue state, we are slightly more likely to this measurement is slightly more likely to output 1 than for the orange state. And this gap is like inverse polynomial. Okay. So the first thing that we do is we do a sort of fairly simple hybrid argument over the bits of x. And what this means is that there is some index I, so some sort of bit of x, such that if I measure the first I minus 1 bits of x, and then either measure the ith bit or not measure the ith bit, right, then the pink measurement also will distinguish these two states, right? So these two states differ by like the measurement of a single bit. And just by a hybrid argument, there's still like an inverse polynomial probability that the pink measurement will distinguish those two states. Okay. So we're kind of isolating somehow the distinguishing advantage of the pink measurement in like one bit. Okay. So this is going to be this observation will lead us to our adversary. So what does the adversary do? So he's going to generate this uniform superposition state, and then measure the second register of that state to obtain the n outcome y. He's going to send y along with this index I that we picked in the previous slide. So this like special index I. And he will then receive a bit b from the challenger. Okay. So then what he does is he measures the first I minus 1 bits of x, and then measures the ith bit of x, okay, and obtains an outcome b prime. If he's lucky and b prime is equal to b, which happens with probability 1/2, right? Then when he measures the first register, when he gets that answer, he just measures the first register and gets an outcome x. Of course, the more interesting case is what happens if the answer is wrong, right? What happens if b prime is not equal to b? Then what he does is he applies the distinguishing measurement from that we assumed existed, and then just measures the first register again and gets outcome x. Just I guess in this case he also measures the first register and gets outcome x. Okay. So clearly in the first case, the ith bit of x is b with probability 1, right? Because we already measured that to be the case. In the second case, what we're hoping will happen, and may not be clear at the moment, is that the probability that xi is equal to b is at least some 1 over poly. And this will be related to the advantage of the distinguishing measurement. Okay. So to see where that is, let's think about the state psi that appears like just before we measure the ith bit of x. So here is the state psi. And we can think about measuring the ith bit of x as a pair of axes in the space. So this is like these two orange states are the projections onto xi being equal to 1 and xi being equal to 0, respectively. So given that, we can then draw the distinguishing measurement in the same circle, right? So there is, this distinguishing measurement, and it's we can assume that it's projective, and so it has some, and it gives you some axes, some orthogonal bases in this circle. Okay. So then what happens is we apply these measurements, right? So first we're going to apply the orange measurement, and this means that the state is going to go to either xi equals 1 or xi equals 0, and that's why we say it goes to xi equals 0. Okay. Then we apply the pink measurement, and the state is going to go to this one of these other axes. Let's say it's this one because this one's closer. Okay. Now, what we need is that when we make the orange measurement again, we're actually going to flip to the other vector, so this xi equals 1 vector. And the way that we show that that's going to happen is we're going to try and show that this angle between the pink basis and the orange basis is not too small. It's at least inverse polynomial. Okay. But this actually is not so difficult to show. So the idea is basically that because there is an inverse polynomial gap, like there is an inverse polynomial gap between the behavior when you measure orange and then pink versus when you measure just pink, right? Remember, this is the distinguishing probability. What this means is that if I just insert an orange measurement after the pink one, then I get the same 1/poly gap at least. And so this means that the orange and pink measurements do not commute with each other. Right. This orange then pink is different from pink then orange, and so this means that they don't commute. And because the measurements don't commute, in fact, they sort of strongly don't commute in the sense that there is an inverse polynomial gap between the two. This means that this angle must be at least inverse polynomial. And what this means is that there is some small but inverse polynomial probability, at least, that if I apply the orange measurement a second time, I'm going to flip to the other vector, so the orthogonal vector. And then I'm going to get the other answer with probability at least 1/poly, and so I've managed to switch the ith bit of x to be 1. So that's the proof. You can feel free to ask me about it at the end. So I just want to leave with kind of an open question for discussion. So obviously the open question is really like, do there exist these like non-collapsing post-quantum CRHFs? Right. So this is a potential route to constructing interesting quantum crypto, including one-shot signatures. However, we have like a number of barriers to getting this result, or you could view them in the positive way as a number of security results about post-quantum CRHFs. It turns out that like at least many of the many sort of natural CRHFs are in fact collapsing. In particular, random functions. So if you model the hash function as a random oracle, then that's going to be collapsing. The itai hash function, this standard LWE hash function, is known to be collapsing. Mark shows that polynomially regular hash functions are collapsing. And I think this is a really interesting result. Actually, it's kind of simple, but insightful. So also like CRHFs with really optimal security, so this means like polynomial over 2 to the lambda security, are also collapsing. And note this like is compatible with Grover because Grover just affects this like what this P of lambda is. So what this means, the takeaway from this, I think, is that non-collapsing CRHFs have to have some kind of structure, right? They can't just be random. And moreover, the structure must make them in some sense suboptimally secure. Like it has to kind of give us like a little bit of an attack against the hash function in order to have this collapsing property. So maybe that can sort of guide us in trying to find candidates for these things. Okay, so that's all the stuff that I have. I would love to have some questions and hear some discussion. Thank you.
Okay, so thank you very much, Nick. And before perhaps I go into questions, maybe I'll double check whether you can hear us okay here. So we can you hear okay? All right, great. All right, thank you very much for your presentation. So we definitely have time for questions. So opening up the floor. Any questions for Nick? Yeah, Justin? Yeah?
If this route that you suggest is a possible route to get to one-shot signatures end up not working out, like, do we have alternative routes?
It's a good question. I mean, sort of. So in some sense, I mean, not exactly. So it's not the case that so it's not the case exactly that like one-shot signatures imply non-collapsing hash functions, but it is close to being true. So there is sort of a related, slightly, a very related primitive, which is called like a non-collapse binding commitment, which generalizes the hash function notion a little bit. So it's like doesn't need to be collision resistant, but it has some other basically that it is a commitment. It's a post-quantum like binding commitment that is that has this kind of equivocality property or this non-collapsing property. So that is implied by one-shot signatures, and it is in fact equivalent to one-shot signatures. And so, if we can't build that, then we cannot build one-shot signatures formally. Of course, like there is another question of like whether this is like the right way to think about it, right? So like maybe we need to like we need a different perspective on it, but at least from a formal perspective, it seems like it's more or less necessary to build something like a non-collapsing hash function in order to get one-shot signatures.
Hello, thank you for the talk. Can you elaborate a bit about the suboptimality statement at the last slide? How suboptimal is suboptimal here?
Yeah, so it needs to be. I mean, if you like change this this expression p of lambda over 2 to the lambda, if it's like p of lambda over 2 to the lambda half or something, right? Then that's already fine. So it just it needs to be like you set so lambda here is the output size of the hash function, right? So like that's like the hash function is from like is into like 0, 1 to the lambda bits, right? And so if it is like only if like finding a collision in the hash function is only like p of lambda over 2 to the lambda half hard, then that already doesn't like that. Then this optimal security doesn't apply.
Thank you.
So it's like I think it's not difficult to come up with functions that have this property. But I guess the way that you normally design hash functions is that you want them to be really secure, right? You want them to be basically this secure, and that is a different goal for post-quantum for non-collapsing hash functions.
So regarding the construction, it seems that random oracle constructions are impossible. Also, like natural constructions from like learning with errors are not plausible. So you mentioned that for this, we would have to look like for like a highly structured problem. Do you have any intuition on what kind of like structure should be looking for?
Yeah. So actually, I mean, maybe Mark will talk about this, but there is like the kind of structure that you want, right? Is that you can like identify this like uniform superposition of pre-images of something, right? And so there are some. I guess I should have maybe written these down on the slide. So there are a couple of candidates for that. which are basically based on some kind of random walk. So the idea is that you have a hash function where you can where you can take this kind of superposition of pre-images state and kind of move it around in a way that it like it's kind of stabilized by something, right? So you like apply some operation which stabilizes like superpositions of pre-images, like or like a certain superposition of pre-images, and like provably does not stabilize single like unit pre-images, right? Like trivial superpositions. By stabilize, I mean, it like more or less maps the state to itself. And if you can do that, then these functions are non-collapsing. So this is the kind of structure that you need.
Likely this is also like a relativized result, right? Like we need some kind of like classical oracle or like some oracle access for like this graph structure.
Yeah. So I mean, we actually don't. I guess this is a good open question. We don't currently have a construction of a non-collapsing hash function relative to a classical oracle. So this is a really interesting open question. So that might be a good place to start, right? Like, can we come up with a classical oracle where we can prove that this is where we can construct we can prove that this oracle is collision resistant but not collapsing.
Okay, thank
so
you.
that we don't know. We also don't know what the relationship is in terms of like maybe it's just impossible to construct non-collapsing hash functions from in a black box way from CRHFs, right? Like maybe there is a way, I guess, maybe there is a way to build like non-collapsing CRHFs from any CRHF, right? What this slide says is that natural CRHFs are collapsing. But that doesn't rule out like being able to kind of do something to them in order to make them non-collapsing.
Right. Okay, thank you a lot.
All right. Any other questions for Nick? Oh yeah.
I guess if you were a betting man, which side would you pick? The existence or non-existence of non-collapsing hash functions?
That's a very good question. I guess my feeling is that they do exist. Like that there is a separation, but the separation probably relies on structured crypto. That would be my bet at the moment. But it is a very low confidence bet.
Perfect. Thank you.
All right. So in that, I think in that positive note, I think it's good we can thank Nick again for his presentation and the Q&A. Thank you.
Thanks very much.